Hi boys and girls, this is lecture 5.7, the topic Integration by Substitution, Part 1. We must develop a technique for integrating composite functions. So far, we've only integrated expressions utilizing the power rule, but let's remember how to take a derivative using the chain rule, then discover how to reverse that process using U substitution. Below is a composite function and its derivative, which was determined using the chain rule. We learned that to take the derivative of a composite function, we had to recognize what the outer function was, which in this case is a quantity raised to the fourth power, and what the inner function was, which in this case is 3x squared plus 2. To take its derivative, we had to first take the derivative of the outer function, 4 times the quantity cubed, and then multiply that by the derivative of the inner function, in this case 6x. Since integration is the inverse operation of derivation, doesn't it make sense that we might see an integrand which looks like this? So the idea would be, if taking the derivative of a composite function results in a derivative that looks like this, there should be integrands of this form, which are the result of a derivative using the chain rule. So we must become adept at recognizing when a derivative was taken using the chain rule so that we can reconstruct the original composite function. Recognizing the remains of a derivative which has been taken using the chain rule requires pattern recognition. Essentially, being able to identify which pieces of the integrand are the original function and which pieces are the remnants of the chain rule. If the original composite function was of the form f of g of x, then the derivative would have the form f prime of g of x times g prime of x. Therefore, we're going to see integrands which fit this derivative pattern, and we'll have to learn to fit the pieces of the integrand to this pattern in order to reconstruct the original composite function. I often call integrands like this a chain wreck, because you can see the remnants of the original function there surrounded by the debris, which is a result of using the chain rule. So in this case, we can see that this piece here must be the inner function g of x, which means this section is the derivative of the main function f prime of g of x. That means this part right here must be the derivative of the inner function g prime of x. And of course, the integral of this results in the original composite function, f of g of x. Antidifferentiation of a composite function. Let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable on its domain, and uppercase f is an antiderivative of lowercase f on I, then the integral of f of g of x, g prime of x dx is equal to uppercase f, the antiderivative of g of x, plus c. We can also substitute u for the inner function g of x. If u is g of x, then du is g prime of x. And the integral of f of u du, where u is representing g of x and du is representing g prime of x, will be uppercase f, the antiderivative of the function u, plus c. And then once again, we see this derivative pattern here in the integral, identifying lowercase f as the outside function, g of x inside function, g prime of x obviously the derivative of the inside function, and uppercase f the antiderivative of lowercase f of g of x plus c. All right, let's try an example, recognizing the f of g of x, g prime of x pattern. So we look at an integrand like this and we recognize this must have been a chain rule, and we must reconstruct the pieces of the original composite function. Notice that we have here probably what was the inner function, x squared plus 1, and right here is the derivative of that inner function. Now I am going to use a u du substitution. If I let u represent the inner function x squared plus 1, then du, of course, is 2x dx. Let's use the substitution for this integral. That means essentially I have u squared du. Now, as you can see, using that substitution gives you a simpler integral to look at, and I am able to easily recognize that adding 1 to the exponent gives me 3, dividing by the new exponent gives me the coefficient 1/3, u cubed plus c is my integral. And then, of course, I substitute the value that we replaced in the original integrand back in for u in the final answer. So 1/3 and then x squared plus 1 quantity cubed plus c is your integral. Now let's check this just for the purpose of demonstration to see if this gives us the original integrand. If my function, my antiderivative here, is 1/3 x squared plus 1 quantity cubed, let's see what the derivative would be. Since it's a composite function, I would need to take the derivative of the outer function, which is something cubed, 3 times 1/3, which is 1, and then that something squared, which would give me 1 times x squared plus 1 quantity squared times the derivative of what's inside, which is 2x. And that, of course, is x squared plus 1 quantity squared 2x, which of course is the original integrand that we were looking at. So we did take the integral correctly. Now let's try an example involving a trigonometric integrand. We're going to fit the pieces of this integrand to this derivative pattern, f of g of x, g prime of x, recognizing that this is a chain rec, the result of a derivative using the chain rule. So at first I look for the inner function, which I believe is 5x. That's the inner function, which means g prime of x is 5 dx, and I do have those pieces here. Now, before I take the integral, I am going to use a u substitution. If u is equal to 5x, then du is 5 dx. Using these values, I rewrite the integral this way: cosine of u du. And again, this simplifies the integral so that I'm able to see clearly how to integrate. This is just the integral of the cosine function, which means my integral will be sine of u plus c. And then, of course, at the end, I replace u with the original value 5x, which means my integral will be sine of 5x plus c. And that is how you use u substitution. The integrands in the previous examples fit the f of g of x, g prime of x pattern exactly. You just had to recognize the pattern. But many integrands contain the essential part, the variable part of g prime of x, but are missing a constant multiple. Fortunately, you can always multiply or divide by the constant you need. Let's apply this principle here. Of course, we look at this integrand and recognize it is a chain rec, the remnant of a chain rule derivative. Here is the inner function, g of x, and that's x squared plus 1. So g prime of x is 2x dx. As we look around the integrand, we see that we have the x dx, but we're missing the 2. As stated up here, you can multiply or divide by a constant, and that's what we need to do. We need a 2, so we multiply the integrand by the 2 that we need, but we have to compensate on the outside of the integral by multiplying by its reciprocal 1/2. Now notice that we do have exactly g prime of x in the integrand. Let's use our u substitution to simplify the integral. If u is equal to x squared plus 1, du is 2x dx. I rewrite the integral, keeping the 1/2 on the outside of the integral, and then I have u squared du. To integrate this, I'll need to add 1 to 2, giving me a new exponent of 3, and then I'll divide by that exponent. So this is going to be 1/2 times 1/3 u cubed, which results, of course, in 1/6 u cubed plus c. And of course, now replace u with the original quantity in the integrand, and your integral is 1/6 x squared plus 1 cubed plus c. That's it for today's lecture. Here is a calculus truism for you to ponder. God bless you, boys and girls.